Hello everyone, welcome to the NPTEL online certification course on fundamentals of food process engineering. We will continue with the viscoelastic properties of food today. So, rheological properties of viscoelastic food that we have started in the last class, we will continue with that. So, again we will see combined mechanical model that can express the behavior of creep. So, this is the spring and dashpot attached in parallel network, just the opposite case of Maxwell where we have connected them in series. So, this is showing the simple creep behavior. So, what happened here is the strain beginning to increase rapidly, but the rate of increase diminishes over time in the form of an exponential decay. So, we can see that since any force we will apply here, immediately the viscous material will respond and try to flow. Now, since the strain or the flow will observe here, it will try to, the strain will try to have similar effect here in the spring as well. So, both will try to expand or strain in similar fashion. Now, because of this linear relation of this spring, it has a linear relation with stress and strain. What happened that it will try to take away some amount of force through it. As a result, this dashpot will show the diminishing rate of the increase in the flow behavior. Okay. So, eventually the exponential decay will be seen. So, here the strains, all strains are equal to each other when they are connected in parallel. So, strain, total strain will be strain in the spring, that is equal to strain in the dashpot, as I said, because of this pressure F applied on it, force F. Okay. And total shear stress caused by the deformation is sum of the individual stresses. So, tau will be tau spring plus tau dashpot. So, tau spring can be signified by spring constant G into strain gamma. However, in the dashpot the stress will be mu into gamma dot. So, another advancement over the Kelvin model we will see here. What happened that the phenomena of creep has been explained by the material by the model, mechanical model, Kelvin-Vickers model, but sometime it has been seen that the proper behavior may not be fully expressed by the Kelvin model. Therefore, Barger model is introduced where some advancement over the earlier model is being done in this form. Okay. So, this is a Barger model where a spring and a dashpot they are in series has been combined with spring and dashpot in parallel. Okay. So, it it will show certain initial elastic behavior when applied to a constant stress sigma. Then it will show exponential retarding that will increase because of this parallel effect of spring and dashpot, and then a perpetual linear increase in the flow will be observed. So, here Kelvin model sandwich between an external spring and an external dashpot. So, E0 and Er is the spring constant of the initial, and here in this combined model eta 0 is the coefficient, the viscosity coefficient of the external dashpot. So, in the Barger model, what happened that initial external spring shows the initial elastic deformation to occur in response to the applied stress sigma, while the external dashpot allows for the perpetual linear increase in strain over time. Okay. So, as long as the applied stress remains. Now, Barger model used to predict the strain as a function of time by this equation, strain epsilon t, that will be equal to sigma 0 initial stress by E 0 plus sigma 0 by E r, okay, into 1 minus e to the power minus t by tau, tau is the relaxation time here, plus sigma 0 into t by eta 0. So, this strain is because of the first elastic component, that is the spring. This part, this exponential decay part, is because of this combined model of spring and dashpot, and the last part is because of this dashpot. So, we have discussed that when we call modulus of elasticity, that is stress versus strain, if we try to have the reverse function, that is strain versus stress, that is called the compliance. So, here J is being used to measure the creep compliance, that is the strain versus stress for the creep test that we are getting. So, here J 0, that is the initial elastic compliance that we are getting, J 1 which is increasing exponentially, okay, that is 1 by mu 0, and then after time t 1 it is decreasing initially because of the elastic component J 0, and then exponentially because of J 1. So, this is the recovery, some part is instant recovery because of the elastic nature, and because of the Kelvin model, the elastic after the elastic material, after the elastic nature, we are getting some exponential decay in the recovery, and some part which is because of the dashpot which is lost completely. So, this will be the compliance over time behavior. Here also if we plot the gamma dot, that is shear rate over time. So, t equal to 0, part 1 which is showing the elastic deformation, and then 2, path 2 or curve 2 is showing the creep flow. Okay. So, that means the flow is increasing continuously. Then recovery of initial elastic deformation, that is 3, and 4 shows the permanent deformation or set. Now, coming to another important behavior, that is dynamic test or oscillatory test. We have seen so far that all the method of viscosity measurement we have seen. So, in that rotational viscosity measurement device we have seen, where a constant angular speed or constant angular motion we are providing. Now, instead of putting angular motion, if we provide some oscillatory motion, and then we can measure the both elastic as well as the viscous property of the viscoelastic material. So, those tests comes under the dynamic test or oscillatory test. So, with an oscillating mode, both viscous and elastic properties of the material can be measured simultaneously. So, what we do is in a sequential pattern or following a sinusoidal wave, we apply the stress and then we try to measure the response of the stress. So, it can be rate controlled, where stress is measured at a constant strain, or stress controlled, where deformation is measured at a constant stress amplitude. So, normally we apply a sinusoidal strain to the sample, causing some level of stress to be transmitted through the material, and then the transmitted shear stress in the sample is measured. So, let us see what happened when we provide a sinusoidal oscillation, that is gamma is equal to gamma 0 sin omega t. So, we will plot it, okay, gamma equal to gamma 0 sin omega t. So, gamma 0 is the magnitude, the maximum point gamma 0, and with respect to the different omega, it is being changed from following the sinusoidal pattern. So, this is the shear strain that we applied, and then what is the stress will be to maintain that strain, that will be analyzed. So, cosine function for the resulting shear rate will be there, that is gamma dot, that is nothing but gamma 0 into omega cos omega t. So, that is gamma 0 dot cos omega t. Okay. So, gamma dot, that will be equal to gamma 0 dot sin omega t plus 90 degree. That means, we can observe a 90 degree shift in the shear rate. Okay. So, shear rate function follows the deformation function, shear rate function gamma dot follows the deformation function which is gamma with a phase shift of 90 degree. Okay. From this equation we can see that, and elastic material will show a shear stress which is proportional to the shear deformation or strain. So, what we want to measure is that we told that we are providing an oscillatory motion. Okay. So, and the material is viscoelastic. So, some part of the elasticity and some part of the viscous nature we need to analyze. So, elasticity is in terms of the force, we know that in case of elastic material the stress will be proportional to the deformation, and in case of the viscous material stress will be proportional to the rate of deformation, right. So, here we are trying to relate them. Okay. Elastic material will show a shear stress which is proportional to shear deformation or strain which is this, and also viscous material will show a shear stress which is proportional to shear rate. So, we will see now the ideal elastic, viscoelastic and ideal viscous. So, these three kind of material when exposed to oscillatory test, what will be their shear stress and deformation behavior. So, shear stress is showing in this plot. For the ideal elastic material, since stress will be proportional to strain, so it will follow by similar kind of plot. So, delta equal to 0. So, delta signifies the phase shift, that is equal to 0. Now, for the viscoelastic there will be a phase shift. Okay. So, that delta we can observe. However, for the ideal viscous nature the delta will be 90 degree. Okay. So, 90 degree phase shift will be observed in case of ideal viscous material, whereas ideal elastic will show delta equal to 0, and in between them any value can be observed in case of the viscoelastic material. Okay. So, the material will have a phase shift between 0 and 90 degree will be taken as the biological material or real material. So, coming to the complex shear modulus. So, it is characterized both the viscous and the elastic properties of a material by measuring the phase shift delta only. So, why this complex shear modulus is that in case of viscoelastic material we do not have a fixed modulus like modulus of elasticity we have in case of the elastic material, ideal elastic material. So, we introduce a complex shear modulus, okay, that is G star equal to G prime plus G double prime. As we have seen that the deformation which is curve 1 and the shear stress observed, that is curve 2, has a phase shift of delta. Okay. Now, G prime stands for the elastic component. We know that G prime it is we may consider it as a spring constant. Okay. So, this is for the elastic component and G double prime for the viscous component. So, the phase shift simply is tan delta, that is equal to G double prime by G prime. So, in any oscillatory test, if we can understand the value of tan delta, we can find out what will be the component of G prime and G double prime in that. Okay. So, if G double prime is that is for the viscous component. So, that is 0. So, that means tan delta is coming 0. So, delta is 0. So, that means it is pure elastic material. So, phase shift does not observe there, and if we are getting the higher value. Okay. So, that shows that G double prime has a significant effect. So, the viscous component will be there. So, that we can identify from the oscillatory test, and in the similar fashion we can calculate also the complex viscosity, where there will be it is kind of a real viscosity and imaginary viscosity. Real viscosity for the viscous component and imaginary viscosity for the elastic component. So, can be G, instead of G we can also express in terms of the complex viscosity. So, another thing is dynamic mechanical analysis. We often do this test in various food material or or different polymer material to understand the behavior, okay, the textural behavior of that. So, what we do here is that instead of the rotational movement that we have replaced by the oscillatory mechanism, here the uniaxial force is being done in the method of oscillation. Okay. So, in which the uniaxial extension and compression is being done and the behavior is observed on a material. So, the force is applied in linear direction only. So, as I said that textural behavior can be observed from that, and assumption over all the analysis we are considering so far is that temperature should remain constant, because temperature has a significant role in viscosity as well as to deform or break down the molecular structure of the material. So, that is why temperature should be taken constant and it should not be very high compared to the room temperature. So, there are certain type of tests can be devised to analyze the effect of increasing temperature on the rheological behavior of materials. We can think of a problem here. The problem has been taken from Shaheen book, where 56 মিনিট আমি ভুলে গেছি মনে টাইমটা না না কিন্তু 5 মিনিট আমাকে কেউ দেখিয়েছিল কি ভুলে গেছি, তাহলে কি করব?
এটা আর কটা স্লাইড আছে? আমি যে লেকচার এত স্লাইড হচ্ছে কন্টিনিউ হচ্ছে,
তাহলে প্রবলেমটার আগে ছেড়ে দিলে ভালো হতো
না। 56 মিনিট হয়ে গেছে, আমি কন্টিনিউ থেকে আপনাকে মাঝে একটা কোন জায়গা কেটে দিতে হবে, এমনিতেই অনেক বড় হয়ে গেছে।
আচ্ছা
না আর কটা স্লাইড আছে?
এটা আর 2-3টে আছে, দুটো কি একটা আছে মনে হয়।
আর কি প্রবলেম 4-5 মিনিট কি হবে?
দাঁড়াও
মানে এই যে এখন যে প্রবলেমটা দেখালেন ওখান থেকেই কত আর কটা আছে?
এখন যে প্রবলেমটা আমি দেখালাম সেটা হচ্ছে 18 নম্বর স্লাইড, তারপর দুটো স্লাইড আছে জাস্ট এটাকে প্রবলেমটাকে বলার, ব্যাস দুটোই আছে।
তাহলে তো তাহলে কাজ করুন
4 মিনিটে শেষ করে দিই, তাই তো?
হ্যাঁ করে দিন ওটাকে, তাহলে মাঝে একটা কোন জায়গায় কেটে দিতে হবে আর কি, তাহলে এটা 1 ঘন্টা হয়ে যাচ্ছে।
হুম।
ওটা কিছু না 9 আপনি 10 করে দেবেন, জাস্ট মাঝে কোন জায়গায় কাটবেন ওটা একটু বলে দিলে, এখন না ওটা পরে বলে
আমি না ওই 5 মিনিটটা খেয়াল করিনি কখন দেখিয়েছে।
তারপরে আপনি আর 2 ফি দেখবেন হয়তো শেষ করে দেবেন, কিন্তু শেষ হচ্ছে না আর কি। আপনি কাজ করুন, আপনি ওই প্রবলেম থেকে স্টার্ট করুন।
হ্যাঁ। ওকে, সো হ্যাঁ আচ্ছা, ওকে ওকে ওকে। Okay, so we will just discuss in short a problem that the creep analysis results were obtained for wheat flour dough by applying a constant stress of 50 Pascal for 60 seconds. So, the stress is given and initial time, the time duration is given on the sample. The data are given in a table that will show. Using creep compliance data, determine the viscoelastic parameter G0, G1, mu1 and mu0 of Berger model. So, Berger model, okay, and this problem is being taken from the Sahin Sharpil book, and so we know that the Berger model is like that. There is a spring, then we have okay, and this kind of force is applied, the constant force, that is constant stress sigma, that is 50 Pascal, right. So, we will see how we will solve that. Let us see the table. So, this is the data table. Deformation of wheat flour dough with time up to 60 seconds. What is the deformation that is given here? Gamma, the deformation. So, Berger model is gamma, that is equal to tau 0 by G 0. This is because of the initial spring stress, okay, because in case of spring we know that tau will equal to G 0 into gamma. So, gamma is equal to tau 0 by G 0 here. Then because of the combined parallel system of the Kelvin model that is there. So, because of that the exponential decay term will be there, tau 0 by G 1 into 1 minus exponential minus t by relaxation retardation time. Here it will be retardation, the creep will be retarding. So, lambda RET plus tau 0 t by mu 0. So, in terms of creep compliance we can write this equation as JT, just we have taken the inverse, that is the strain versus stress. So, divided by tau 0 we are getting this JT equal to J 0 plus J 1 1 minus exponential minus t by lambda retardation plus t by mu 0, okay. And then what we will do, we will plot this, we will plot first the creep compliance with respect to time, and we can get that it is initially there is a curvature exponential increase and then a little bit of straight section. So, from the straight section data, if we plot that in the straight section minus the initial stress that is J 0, then we will get this equation by linear regression, and from this data J minus J 0 with respect to time we can get the intercept and slope value. So, we can get the values of J 1 and mu 0. Okay. Again, which is the non-linear part or the or that is the gradual increase, that section we will plot with respect to time, so that the part of the Kelvin model, the parallel arrangement of the spring and the dashpot, that section can be calculated, okay, from this chart. And lambda retardation will be mu 1 by G 1. Mu 1 is the viscosity coefficient of the dashpot 1, and this is the spring constant of the spring 2 that is attached in the parallel with the dashpot. So, we are getting the retardation time as 5.21 second. So, we will just put all the values that we are get from here and also from the this section, that is from the curve section with respect to time. So, we will get finally this plot. Okay. So, first this creep behavior here, that we are getting J 0, okay, as we can see the equation. See the equation J 0, then was J 1 and lambda t and mu 0. Okay. So, here we are getting J 0 from this plot. Then once we get this value, so J 1 will be calculated from here. Okay. So, J 1 we are getting J 1 we are getting, and we'll calculate the J 1 we are getting, and then from 1 minus exponential minus t by here the lambda retardation time. So, retardation time 5.21 second, we will plot it here, and finally mu 0, which is coming from the inverse of that slope that we are getting. So, using using that we can find the equation of the creep compliance of the dot sample. Okay. So, this is how we solve the phenomena of the creep from the compliance versus time behavior. So, we will stop here, and as we are ending the chapter over here, that is the rheology of food. So, next we will in the next class we will start a new chapter. Thank you all.